All right, let's get right into it. You know, for over 100 years, pretty much all of modern math has been built on one single idea, set theory. It's the bedrock. But what if there was another way? A whole new language that could not only rebuild that foundation from the ground up, but also connect these totally separate worlds of math. Well, that's exactly what we're talking about today, homotopy type theory.
So, let's be clear, we're starting with a massive idea here. This isn't just some new theorem or a clever little trick. Nope, we're talking about a fundamental shift in how we see things, a way to bring all these different worlds of thought together under one roof in one single language.
And the claim here is, well, it's incredibly bold. The folks behind HoTT, that's what we'll call it, are proposing what they call a univalent foundation. And all univalent really means is that if two things are logically the same, you can just treat them as identical. Simple, right? But the implication is huge. They're not just suggesting an improvement. They're offering a complete replacement for set theory, the very foundation that's held up math for a century.
Now, this is what's so wild about it, the sheer scope of this thing. HoTT is like a universal translator for math. It builds a bridge between four fields that honestly don't always talk to each other. You've got the geometry of spaces, the pure rules of logic, the nuts and bolts of computer science, and even the high-level structures of category theory. It pulls them all together. It's an absolutely incredible synthesis.
Okay, so how does it actually work? To really get the magic behind HoTT, we have to look at its core idea. And it's a big one. It completely redefines one of the most basic concepts in all of mathematics, what it means for two things to be equal.
So in this new world, you think of a mathematical type, like, say, all the natural numbers, as a kind of space. And a proof that two things are equal, like proving that 2 plus 2 equals 4, well, it's not just a statement anymore. It becomes a literal geometric path that connects the point 2 plus 2 to the point 4 inside that space. It's a tangible connection.
And this is where you really see the huge shift in thinking. The old way, equality is black and white. Either A equals B or it doesn't. End of story. But in HoTT, equality suddenly has, well, it has texture. It has depth. Think about it. There can be lots of different roads to get from one city to another, right? In the same way, there can be many different proofs that two things are equal. And each one of those proofs is its own unique object.
Okay, but this beautiful geometric picture, it sounds great, right? So intuitive. But it's hiding a really deep philosophical problem. A problem that kind of challenges whether it can truly be a foundation for mathematics at all.
And to figure that out, we have to step back and get a little philosophical for a second. What does a foundation for math even need to do? I mean, what does it take for a system to be considered truly, well, foundational?
Well, a true foundation has to be what's called autonomous. That means it has to build the entire house of mathematics from scratch. From the ground up, it can only use really basic pre-mathematical ideas, things you don't need math to understand. It can't, borrow a bunch of fancy tools and materials from the skyscraper it's supposed to be supporting.
And that brings us to the core problem. That standard explanation of HoTT, the one with all the spaces and paths, it's circular. It's using ideas from a really advanced field of math to explain the very system that's supposed to be the foundation for that advanced field of math. It's like trying to stand on your own shoulders. It's relying on the very thing it's supposed to be holding up. So if the spaces and paths idea is circular, how do you fix it? How do you build a truly solid base? Well, a couple of researchers, Ladyman and Presnell, came up with a really elegant solution. It's a philosophical shift. What if we stop thinking about types as spaces and start thinking about them as concepts?
Now, this change sounds subtle, but it is incredibly powerful. Instead of a type being a space, think of it as a general concept, like natural number. And a specific thing in that type, like the number 2, isn't a point in space. It's the specific idea of 2 viewed as an example of the general concept natural number. And here's the kicker. The idea of a concept is something we all understand without needing any math. So this interpretation is totally self-contained. It doesn't have to borrow from anywhere. It can start from zero.
Okay, so this whole debate, it's not just some abstract exercise for philosophers. This has led to a real, living, breathing project that is actually changing how math gets done, right now, in the 21st century. HoTT has gone from being just a theory to a hands-on, collaborative tool. I mean, its main textbook, the HoTT book, isn't some dusty old volume. It's an open-source project on GitHub. Anyone can contribute. And, this is the really important part, the ideas are turned into actual code. This allows mathematicians to write proofs that a computer can check, line by line, for mistakes. It's incredible.
And believe me, this isn't some niche little hobby.
The paper that explains the HoTT code library, it's on a platform with more than 25 million users. This is a huge, active, and growing research community all across the globe.
So, where does this all leave us? What does this mean for the future of mathematics?
This really is the big question to leave you with. What happens when a mathematical proof can be built, checked, and trusted by a computer? A foundation like HoTT is built for computers. It doesn't just give us new ideas, it gives us new tools. We're moving into a world where a proof isn't just an argument written in a journal anymore. It's a piece of software you can run, test, and know with 100% certainty is correct. It's a future that could totally change what it means to be certain about a mathematical truth.